All right. Well, good afternoon or morning or whatever it is. I'm trying something a little different. I'm not sure how it's going to work out, so hopefully it works out well. So don't mind this random picture of this guy right here in the corner. This is physics lesson 4.1, free fall. First thing we're going to talk about is force. So although we're not going to cover force until a later chapter, I want to introduce it because it's kind of important when we're dealing with free fall. So force is going to be a push or pull, and there's lots of types of forces: force of friction, force of air resistance. But what we're going to focus on right now is the force of gravity. Now, force tries to change the motion of an object, and it does not have anything to do with how fast it's actually going. All right, so free fall. An object is in free fall when the only force acting upon it is gravity. So examples of this would be a ball being dropped off a building, a ball which has just been dropped down off a building, and a ball in which is thrown up into the air. All of which only have the force of gravity on the ball. Acceleration of gravity here on Earth, we have it as negative 9.8 meters per second squared, but in this class you can just round that up to negative 10 or round it down depending on how you want to talk about it. Notice that on different planets it's different. So the moon has a negative 1.6 acceleration of gravity. So if you were to drop something on the moon, it would fall to the surface in less time than it would here on Earth. On Jupiter, it has a larger magnitude of acceleration of gravity, still with the direction down. So if somehow you get to Jupiter and we were to drop something, it would fall much faster. Remember, we're going to talk about force later, but for right now, acceleration of gravity is not the same as force. It's just what an object is accelerating at. All right, there's a really cool video right here. You should look it up. It's Gravity of Falling Objects on the BBC, and it shows a ball and a feather being dropped at the same time with and without air resistance. Now, we're not going to deal with air resistance in here, so we're not going to have to calculate it. So, acceleration of gravity, what does this mean? It means for every second object falls, the velocity will decrease by a factor of 10, and the speed will increase by a factor of 10 because acceleration of gravity is negative 10 meters per second squared. So this is going to be our constant slope from now on when we're dealing with projectiles. All right, let's do a quick practice problem. I feel purple today, so I'm going to use purple. We have Sally. She's going to drop a ball from rest, which means that her velocity initial is 0. And we're going to fill in the missing sections of this chart. So let me open up another page real fast. So our velocity initial equals 0. The time for the first one is 1 second. And we're trying to figure out velocity final after that 1 second. Our acceleration of gravity is constant at negative 10 meters per second squared. So we can use our negative 10 equals Vf minus Vi equation over time. So let's figure out Vf. So we have negative 10 Vf minus 0 over 1. That's a really bad 1. 1. And we should get Vf for 1 second as negative 10 meters per second. If we were to go ahead and do that same problem, only now use time as 2, we should end up with a velocity final that is negative 20. And this is a consistent pattern that you're going to see whenever we have a dropped object. It should change by a rate of negative 10. Hooray! All right, next problem here. We have Roy throwing a ball down. So now we're throwing the ball down, so our velocity initial is not 0. Velocity initial is negative 30 meters per second. Time is still 1. Velocity final, we don't know. That's what we're looking for. Acceleration of gravity, still negative 10. So now, we go back to that same formula. Velocity final is what we're looking for. Minus 30 divided by 1. So negative 10 equals Vf plus 30. So when we pull it over to the other side, Vf equals negative 40. There we go. And if we were to plug in 2 seconds, we should get negative 50, negative 60, negative 70, negative 80, negative 90, which should make sense because we're giving it a little extra oomph as it goes down. All right. Next problem here. We have Roy. He's going to throw a ball up at 30 meters per second. So now our velocity initial is positive. 30 meters per second. Time is 1 second. Acceleration of gravity is still negative 10. So negative 10 equals Vf minus 30 over 1. Negative 10 equals Vf minus 30. So we end up with 20 equals Ef, 20 meters per second. And that's positive, so still going up. If we were to plug in 2 seconds to that same formula, it would go down again. So this would be a plus 10. 3 seconds would be 0. So the path, looks like this, is now reached the height, and our Vf equals 0. And it does so in 3 seconds. Then it starts to fall back down. So negative 10, negative 20, negative 30. All right, so those are velocity. The tricky part has always been displacement. So what about displacement? So we're still using these same formulas. Delta x equals 1/2 Vf plus Vi times t, our blue equation, our green equation, only now we're dealing with vertical displacement. So instead of using delta x, we're going to look for y. So these formulas, we have to change them slightly to account for delta y. It's still the same formula, only now we're including delta y. All right, so let's do one practice problem here. This is the same problem that we had to start with. So we know our velocities. Those are previously put in there. Negative 20, negative 30, negative 40, 50, negative 60. So if you're wondering how I got those numbers, just rewind a little bit. That was the first quick practice that we had. Quick. Now we need to solve for delta y. Because we dropped it from rest, our velocity initial is 0. So we can use the delta y equals 1/2 acceleration times squared plus velocity initial times time. Because the velocity initial is 0. So we don't have to worry about that part of the problem. So 1/2 negative 10, 1 squared equals delta y. So it should have fallen down 5 meters. Yay, 5 meters. Then let's go back over here. Change this 1 second here for 2 seconds. And now we have negative 5 times 4 negative 20. Come back, change out that 2 for 3. This turns into a 9, negative 45. And you just keep going, substituting in those t's for each one. All right, so I'll leave the last one to you. Same idea, only now our velocity initial is not 0. It's positive 3. You can still use the same equation because we're given time. Normally we don't like to use this equation, but we have time, so that's going to work. Just remember, this is negative. It's going down, down, down to the ground. All right, stay tuned later on. 4.2 and 4.3 should be coming up later.